We've been talking about the termination of El Niños as if it's some smooth process. Obviously, every El Niño terminates differently. 1997-98 somehow produced an amazing signature, and it was caught in its full glory in the newly launched ocean color satellite called CWIPS. If you just looked at sea surface temperatures at the end of the 97-98 El Nino, weekly SST anomaly SSTs here going from 20 cold to warm, May second week, May third week, fourth week into June and July, sorry, June first week and second week. You can see that you see some cold temperatures replacing the very warm El Nino temperatures, and they begin to get colder, extend more westward, get stronger here. This turns out to be a very unique process that happened. And then you see some tropical instability wave-like structure. Nothing dramatic other than that this transition seems quite rapid in 1 or 2 weeks. But the processes associated with them were quite remarkable. If you looked at February 1998 in ocean color, you can see that the entire patch of the elevated ocean color was clearly shifted to the north of the equator. Here is the equator, and this is clearly to the north of the equator. Here it's more spread out in the cold tongue and on the equator. You know that ocean upwelling is on the equator, ocean color is on the equator, and it's on the only quantity that you can see from, only variable you can see from space that actually shows the geographical equator, because rain and winds and or sea level, etc., they are a maximum or minimum of the equator. The meteorological equator is what ITCZ is called, which is clearly seen in rainfall and so on. So what happened that pushed this chlorophyll bloom to the north of the equator instead of on the equator? It turns out that the processes are quite remarkably unique, but it should be known to us, because remember, we keep saying El Nino peaks in December, January, February, during which time sun is to the south of the equator, so the convection that has moved eastward will be maximum south of the equator. Winds will be shifted as well, and the heating actually attracts winds convergence into it, and you would expect that there are northerly anomalies going into the maximum heating. So the termination started in January 98. You still have warm SST anomalies. There is something special done with this in the way it is reconstructed. So we are looking at sea surface temperatures plus the zonal velocities associated with the Kelvin and Rossby waves. It's a way of doing things, but I'm just using it to show that by February 98, you're beginning to have a divergence along this side. So you can see the SST anomalies are clearly shifted to the south, and it's spreading towards the east. In a separate paper, we showed that this is related to the tropical instability waves and so on. It doesn't matter, but you can clearly see that there is a divergence happening here with a maximum SST and minimum in OLR. So maximum convection is located clearly to the south of the equator. If you want convergence into it, then you will have northerlies, southerlies, and easterlies and westerlies in an anomalous sense. So by April 98, you can see that SST anomalies have moved away from this site, and the cooler temperatures begin to appear. These are reconstructed complex multivariate UFs of SST and zonal velocity. So you have to be careful about interpreting them as pure SST anomalies, but still they are associated with the El Nino. So suddenly this cold blob of SST pops up, and you can see it occupies the region around the equator and grows and becomes much colder. The whole thing happens very quickly. July, August, rest of the year of 1998 was one of the strongest La Niñas. So very strong El Nino it was followed by a very strong La Niña. The transition is what we are interested in. So that's August, and you can look at the impacts here. The seasonality is critical here. So rainfall anomalies positive clearly to the south of the equator, because sun is to the south, the anomalous convergence zone and the rainfall have shifted to the south as well. So they begin to shift westward, eastward as the El Nino grows. By the time El Nino is maturing, the entire belt of positive rainfall here is to the south, and you have negative rainfall anomalies on the other side, and you can clearly see the sea surface temperatures are nearly symmetric except for the coastal regions where you have obviously Niño 1+2 being warmer, and you can see these wind anomalies converging into the rainfall convection centers, and you can see how the upwelling happened into this zone where temperatures dropped very suddenly in a few weeks by a huge amount. Cooling sea surface temperatures is not easy. You cannot do it by picking heat from the ocean by the atmosphere, because you will have to pick thousand watts per meter squared or more, which is not very easy. The heat flux anomalies are hardly order 100 watts per meter squared, but you can see the structure. The undercurrent is there. You have upwelling happening into this zone in the central eastern part. It just happens to occur at that region. Not every El Nino will work the same way. So the waters, cold waters, came obviously from the west. They were not cooled at the surface, but they were supplied from below. So the question is, how did such cold waters get to the tropical Pacific? If you want to pull cold waters from below, you'll have to go very far deep, but you can bring it from off the equator and pump it up here if you have the advection and upwelling processes happening. So a model output was used to look at it. So you are looking here at depths in colors, so you can see the lighter color, the dark red colors are at close to the surface, but the bluish magenta colors are deeper down to a couple of 100 meters. So here you are looking at January, 0106 is the US way of doing it. So 9/11. So this will be January 1993. As you integrate forward, so these are essentially like back trajectories being projected forward. So the waters are coming in. Here you are at 140 meters below the surface, coming from both sides, and it is getting closer to the surface by January of 1997, about 130 meters below. By July of 97, they are close to 100 meters. And sorry, I have to be sure. This is June 01. So this is anyway, never mind. By June 1998, yeah, this is 98, that is 97. December 97, June 98. So you can see that the cold waters came from far away, made the trek over several years, and became available to upwell here in the early summer of 1998. So these colors are close to the surface. So the recharge-discharge process is very clearly visible here. The recharge process is such that you begin to pull in cold waters all the way towards the tropics and the eastward movement here in the undercurrent, and then it gets pulled up. I hope that's clear. So you can look at a little bit more. OLR, where it's very negative, is where deep convection is happening. Negative rainfall anomalies here, so positive OLR anomalies, and you can see sun is to the south, so maximum convection is to the south. Clearly there are northerly wind anomalies running into the convergence for the convection to happen. When you blow winds into the equator, because it's a dynamical boundary, Coriolis changes sign, so you cannot push waters across the equator easily. So waters pile up, and you get a pressure gradient northward, so flow will actually go north, and that's what shifted the entire band northward. I'm getting a phone call. Let me pause this for 1 second. Okay, sorry about that. Hopefully I'm recording. So here we go again. We are talking about pushing waters against the equator, building a pressure gradient northward and pushing the entire upwelling system to the north. So the ocean color is to the north, and you can see that there is also sea level maximum to the north associated with the shallow thermocline. And the winds, you can see these are from one of the TAU arrays and the tropical TOGA arrays, tropical atmosphere or global ocean array, and this is for February 98 to June 98, and you can see northerly wind anomalies. As soon as the cold water popped and the convection died, the wind anomalies died away as well. When you make such quick transitions in the wind, they project onto instability waves in the tropical Pacific. So you can see here, this is going from May 8th to June 16th here, and June 17th to July 19th. And in the sea surface temperature, nothing was visible clearly, but in the chlorophyll, you can clearly see the tropical instability waves which propagate eastward and get stronger. And this shows how the entire process of vertical shear in the currents in the ocean and horizontal shears in the currents together produced tropical instability waves, which was not as obvious in the SSTs, but it clearly got manifest in the chlorophyll. Though, this is further into August, very clearly shows how the entire termination evolved. Just because it went from strong El Nino to strong La Nina and the sudden collapse of that convection center and the northerly anomalies, it got registered into the new satellite data that was being collected. Not all terminations happen this way, so obviously I have been looking at other terminations to see if such a dramatic end will occur again, but hasn't happened. But if you are watching Ocean Color this year, next year when the 2026 strong El Nino terminates, you may see again something dramatic like this. So keep your eye out if you're a remote sensing person. Okay. See you in the next podcast. We're getting close to finishing the story of El Nino. I'm just randomly putting things in place because so many posts are being made and I'm not sure all the details are being captured. Okay.